Hello, ladies. Today we're going to introduce the topic of acids and bases. So this starts Unit 7 for us. And what we're going to start with is we're going to start by just talking through some properties of acids and bases and how we define those acids and bases. So let's start with acids. So acids are substances with the following properties. So they have a tart or sour taste. Think about lemon juice, orange juice, vinegar. Those are all acidic liquids. So if you can think about that taste as being a distinguishable property of an acid. Acids are also what's called electrolytic. So electrolytic means they conduct electricity. Acids also cause indicators to change colors. You might not yet know what an indicator is, but we'll talk about those later in this unit. And acids also react with some metals to form hydrogen gas. So next would be our properties of bases. So bases, okay, taste bitter, a little differently than our acids taste. Bases have sort of a slippery feel to them. If you were to have some on your fingers, they would feel sort of slippery. Bases will also change the color of an acid-base indicator, but that would be a different color than an acid would turn that indicator. And bases can be strong or weak electrolytes in aqueous solution. So again, electrolytes are those substances that do conduct electricity in solution. So those are some properties of bases. And then there are three different acid-base theories that we're going to talk about, and we're going to go through each individually on the next slide. And those are Arrhenius, Bronsted-Lowry, and Lewis theories, one of which is my favorite theory, and I believe most people who study chemistry also hold on to that belief as well. So let's move on to that. Okay, so let's start with the Arrhenius acids and bases. So Arrhenius defined an acid as a substance that will ionize to form hydrogen ions. So those hydrogen ions, right, are an H plus. And when we talk about acids, often those H plus ions are referred to as protons. And it's because of that +1 charge. So for instance, HCl, hydrochloric acid, when it ionizes, so ionize simply means it breaks apart into the ions that make it up. It breaks down into an H plus, and there's that proton, and a Cl minus, a chloride ion. So you can think about acids as being, right, these are words you may have never seen before, but monoprotic, right? So mono means one. Diprotic, so di means two. And triprotic, tri means three. And if you'll notice that those numbers are the same number of hydrogen ion that are in each of those formulas. So the HCl only has one H, the H2SO4 has two H's, and the H3PO4 has three H's. So that's what those monoprotic, diprotic, triprotic mean. One proton, two protons, three protons. Okay, so under the Arrhenius theory, bases are defined as substances that ionize to yield hydroxide ions. So that OH minus ion. So for instance, sodium hydroxide, or NaOH, when it ionizes, again, breaks apart into the ions that make it up, you get an Na plus, so a sodium positive ion, and that OH minus. So far, right, we're looking at two things here. We're looking at acids being identified by having that H in them, that H plus. And we're looking at bases as having that OH minus. So moving forward, when you see a chemical formula, if that formula starts with an H, right, we can go ahead and identify that as an acid. If you're looking at a chemical formula and you see an OH, you can go ahead and identify that substance as a base. Okay. So another theory on acids and bases, and I'm not a huge fan of the Lewis acids and bases theories. They're a little tough to understand, but you can think of it sort of as the opposite of Bronsted-Lowry, which we'll get to in a minute. So Lewis acids and bases claim that an acid is a substance that accepts a pair of electrons during a reaction, and a base is a substance that donates a pair of electrons during a reaction. So you would think if an acid is accepting a pair of electrons, the acid is the thing that during a reaction becomes more negative. And if a base donates a pair of electrons during the reaction, you could look at the base as the thing that becomes more positive during a reaction. But again, moving forward, right, we're not really going to, other than knowing this definition, we're not going to do much with the Lewis acids and bases theory because of this point here. So the Lewis theory is more general than Arrhenius or Bronsted-Lowry, which makes it a little harder to understand. So now we can move on to my favorite, dun dun dun, and that would be the Bronsted-Lowry theory on acids and bases. So Bronsted-Lowry defines an acid, and let me get out my trusty highlighter here. My favorite color for my favorite acid and base definitions is the acid is a hydrogen ion donor. So an acid, again, it has that H plus, it has that hydrogen ion in its formula to give, and a base is a hydrogen ion acceptor. And the reason that this is a better definition is because there are substances that don't necessarily have that OH in their formula that still act as bases. So this is kind of a bigger umbrella for our acids and bases to fit under. So here we go. Basically restating what I just said in a fancier way, all of the acids and bases included in the Arrhenius theory are also acids and bases according to Bronsted-Lowry. So again, what that means is that Bronsted-Lowry is a bigger umbrella and more of our substances that we know are acids and bases actually fit under that definition. So some compounds not included in the Arrhenius theory are classified as bases in the Bronsted-Lowry theory. For instance, probably the most commonly known substance that is a base is NH3. Okay, and NH3 would not fit under that Arrhenius theory of having the OH. So NH3 is a base. It's a pretty common base, and it would not have fit under that first theory that we talked about. So I love using charts, and this one sort of very nicely summarizes the three acid-base theories in a less complicated way than the way we just defined it. And again, I'm going to put a star next to the Bronsted-Lowry theory here because that is the one that I tend to follow and the one that I want you to follow moving forward. But it's important to know the other theories at the same time. Okay, so with that said, right, we're going to talk about something called conjugate acids and bases, because in an acid-base reaction, right, here we have our base, which is ammonia, and H2O, which functions as an acid, and we'll talk about why that is right down here in this section once we get past. Every acid and base in an acid-base reaction also has a conjugate acid or a conjugate base. So for instance, okay, NH3 is a base. NH3 is a base because in a reaction with an acid, it accepts a hydrogen ion. So what does it look like after it accepts that hydrogen ion? It looks like this. So if we have an NH4 plus, and if you guys remember studying your polyatomic ions, that's the ammonium ion. So ammonium is the conjugate acid of our base ammonia, right? And it becomes that conjugate acid by accepting NH plus. Okay, so NH3 in this case is our H plus acceptor, okay, to become NH4 plus. Now, what does this mean for H2O? So H2O goes from H2O to OH minus. So it has lost an H plus. So when it loses an H plus, right, it becomes its conjugate base. In this case, its conjugate base is the hydroxide ion. So, right, what happened? This acid, H2O, gave its H plus to NH3. So when you have an acid-base reaction, you want to figure out what is the thing that accepts a hydrogen ion, right? So going from this side to this side, right, we obviously in the change of formula, you added an H plus to NH3, right? And in going from H2O to OH minus, you lost an H plus. So that means that the H2O was our hydrogen ion donor, and our NH3 was the hydrogen ion acceptor, making it a base. Okay, and then here you have some fancier definitions if you wanted to jot those down into your notes. But lastly, the conjugate acid-base pair consists of the two substances related by the loss or gain of a single hydrogen ion. So the things that I drew the lines between would be your conjugate acid, your acid conjugate base pair, and your base conjugate acid pair. Okay. So that brings us to an important point. Okay, water, we're generally told, is a neutral substance, and it does fall kind of in the middle of our pH scale. We'll talk about the pH scale in another lesson. So H2O, depending on what it's reacting with, can act as a hydrogen ion donor or acceptor. So it can act as an acid or a base. If it's reacting with something basic, in this case, NH3, right, it's more likely to act as an acid. If it's reacting with something acidic, like HCl, it's more likely to act as a base. So in this case, right, H2O is acting as our acid, and it donates an H plus to NH3, making it NH4 plus. And in our second reaction here, H2O is acting as our base, and it accepts a hydrogen from HCl, becoming H3O plus. So H3O plus has a fancy name, and that is the hydronium ion. So the hydronium ion is the conjugate acid of water when it's acting as a base. And any substance, for instance, water is an example, any substance that can act as both an acid or a base is said to be amphoteric. So amphoteric is an important vocabulary word there to know. Okay. So lastly, we're going to do some examples of conjugate acids and bases. We're going to take a look at these reactions. So I have 3 examples here. We're going to take a look at these reactions. We're going to identify the acid and the base, and then we're going to attach it to its conjugate base and conjugate acid. So HF, just based on the definitions that I gave you to start with, right? What do we have in this formula? So in the formula HF, we see that it starts with an H. So immediately we should be thinking acid. And let's just make sure that it fits the definition. So if it's an acid, it should be donating a proton. So if you look at the other side of the reaction, right, we go from HF to F minus. So HF did in fact donate a proton, right? It lost a proton to go from HF to F minus. So that's your acid, and F minus is the conjugate base that goes with it. Okay, so if HF gave up a hydrogen, that means that water should have accepted a hydrogen, and let's make sure that that happened. So water goes from H2O to H3O plus. So it did in fact go up by one hydrogen ion, okay? So that makes water our base, and H3O plus, which we know as the hydronium ion, is our conjugate acid. So that's all you have to do with these reactions, is you're identifying your acid and your base, and then you're looking at your products and you're identifying the conjugate acid that goes with your base and the conjugate base that goes with your acid. So let's take a look at this example. Okay, so we have an OH minus and we have an HCN. So again, we see the OH, the hydroxide ion. So you should kind of be thinking base, and then you see HCN, and you see that it starts with an H plus ion, so you should be thinking acid there. And let's just make sure that we see that happening. So HCN goes from HCN to CN minus. All right, so it did in fact give up a proton. So to go from HCN to CN minus, it donated a proton. So that makes HCN our acid and CN minus our conjugate base. Right, and let's make sure our OH gained a proton, which in fact it did, going from OH to H2O. Okay, so that makes OH our base, and H2O is our conjugate acid. Okay, so last example, we have HBr and CO3 minus 2. So which one of these has an H to give? It would be HBr. So we can go ahead and assume that that's our acid. And we're going to take a look at what happens to HBr going from reactant to product side. And it does, in fact, lose an H. So that means it donated it to the CO3 minus. So that makes HBr our acid, and that makes Br minus our conjugate base. And then CO3 minus 2 does, in fact, gain a hydrogen, right, going from reactant to product side. So that makes CO3 minus 2 our base, and HCO3 minus our conjugate acid. And notice what's happening. So this goes back to the Lewis theory. Notice what's happening to these substances when they go from reactant to product side. So HBr, right, is the thing that becomes more negative. So here, right, it doesn't have a charge, so it goes from neutral to negative. So it goes down in charge. It becomes more negative. And CO3 minus 2 goes from a minus 2 to a minus 1. So that actually goes up in charge and becomes more positive. So that's what the Lewis theory of acids and bases is based on, kind of that changing in charge of our substances as we go from reactant side to product side. But again, I think personally the easiest thing to see and to recognize are what's happening to those hydrogen ions as you go from acid to base to conjugate acid to conjugate base. So keep that in mind and see if before you even look at your product side, if you can make an educated guess as to which is your acid and your base, just based on what substance has an H to give in it. All right, thanks for listening. I hope this helps.